please raise your hand if you have any questions.
Oh, can I ask something? I don't know how to raise hand today. I don't know why. Hello?
Yeah, you go ahead.
Yeah, so I have a question about the hole in the antiferromagnet background. So is there any prediction you can make based on the constraint of the motion of the single hole and a double hole? I mean, for example, the prediction about the transport.
I mean,
with doped TJ model, for example. I mean, the transport of a whole doped TJ model was actually studied a lot in quantum matter. So I wonder whether there's any prediction that one can make based on the motion.
We made some predictions in the paper that I have to remind myself, but I think there's a little bit of a difference because the TJ model will have J perp the same as JZ, right? So we're in the limit where JZ is bigger than J perp. That's important. The Ising coupling is bigger than the exchange. And one thing about mobilities, for example, if you're interested in transport, mobility scales with the inverse of the effective mass. So effective mass of the fracton is infinite. The dipole is not infinite, as a finite mass, and we computed that in that paper. I forgot the number. So, depending on your regimes, you can look at the mobility and you can say something about transport from that perspective. I don't know if that answers your question.
Sort of. So actually, so the observation works better when it's the Ising limit, right? I mean.
Yes, because once, I mean, for small, for small J perp, that means, let me share my screen again, if that's okay. So this is the story. So let's just look at, for example, this picture, right? So when this comes here, right now, even if I have spin exchange, nothing can happen that will remove this frustration. So you see this bond is frustrated, this bond is frustrated, this bond is frustrated. So the spin highlighted is unhappy. So with the spin exchange, nothing happens. So I have some parametric regime, but if I hop again, and then this spin here, the blue spin down comes here, these two spins now are nearest neighbor, and spin exchange, if it's nearest neighbor, can allow them to heal the background. So the hole now can be sitting there and be satisfied, right? So spin exchange is not good for this story if it's very large, right? Does that make sense?
Oh yeah. I think that the hole can also hop to the second neighbor, right?
Sure.
So that doesn't seem so bad for the energy.
Yeah. Yeah, and you're saying if it comes here, for example, then that comes here, and the background is still annoyed, and the hole will be there, and so that is still energetically expensive. Yeah, that makes sense too.
Yeah. So
there are some predictions. I'm sorry, I forgot. To be honest, I forgot the details now, but we can discuss offline, and I can.
Oh, sure. Yeah. Okay. Thanks.
Thank you.
Yeah, Dang, you can go ahead and ask.
Yeah, so I have a question for the first talk. So I have a few questions, and the first one is, did you consider the quadruple?
No.
Not yet.
Not at all.
Another question is, so you say that you have the approximately for 2D and 3D. Can you give us some picture for 3D? How's it?
Okay, so I mean, I maybe I'm not being very careful. Let me share my screen again. So of course, if you're on the square lattice or a cubic lattice, so simple lattice in 3D, the same story applies.
Yeah.
Right. So that's essentially what I meant to say, right? Because essentially the point to make or to appreciate from the 2D limit is that there is, let me go to this. Yes, there's a very high order process, a very high order loop. You see, so what happened here is this hole made a complete loop and came back and then continued and then ended up here. So that's a very high order process that happens in 2D and 3D. If you have your typical bipartite square cubic lattice. More complex geometries, then that's another question. That's something, you know, that one has to look in depending on the details. So at very high orders, the fractal is localized.
So can you think
sorry.
So can you think for like different type of lattice in 3D that you can relax this constraint?
Yeah, so we're looking at things right now. I'm looking at things with someone. I don't have much to say right now. It's still in progress. But I think you need to play, just let me put it this way, you have to play with, you need to make certain bonds antiferromagnetic and other bonds ferromagnetic. That sounds strange in the, you know, in the offset, but there are actually recent experiments where they have this situation. It's like layered materials, right? So along one direction, couplings are ferromagnetic, along others, they're antiferromagnetic, and you can get more interesting stories. You know, you can, for example, completely localize the hole. You can make the hole move along a line.
I see. Thank you.
Welcome.
Any other questions? All right, if not, then we'll have a 5-minute break before the next session.